Hi, I'm Josh Pennell with IOActive, and this is Mike Davis, and we're going to talk a little bit about some of the hypervisor research that we've done recently. Basically, the way that we've approached this certain subject is that if you're sitting in your organization and your management team comes to you and says, hey, we're looking into deploying our infrastructure into the cloud, or we're looking to develop an internal private cloud for the organization, some of the things that you probably want to think about and from a security perspective. So this is particularly applies to IaaS. All right. So a little bit about us. Won't belabor this too much. We've been around since '98. One of the things that is kind of important for this talk, I suppose, is that we're one of the few firms that actually have looked at all three major cloud computing platforms. Some of the major companies that are close and dear to your heart. We've reviewed their systems. High-end software and hardware review company, been around for a bit. So here is our agenda for today. We're going to go over the history of the hypervisor. For those that don't know, raise your hand if this gets boring, but we find it kind of fascinating because, of course, it's kind of revisiting the past to determine what's going to happen in the future. We're going to go over the architecture of hypervisors and why you should care from a deployment perspective, the attack surface of the hypervisor, some of the attacks that are known now, and some of the attacks that might happen in the future. And then some of the summary of what we've talked about with some remediation paths forward. So here's the hypervisor history. For a lot of you probably understand, but hypervisors are certainly not new. Stemming clear back to 1960, we've got the IBM M44 that's fired up. Mainframe application. It had para-virtualization, so it wasn't complete full hardware virtualization yet. It was a hybrid. And then in 1961, they found that the CTSS system needed to have a backwards compat capability for the 7094 for Fortran. And then moving on from that, those are, Robert Creasy didn't really think that these systems are true virtualization systems, and then he moved on to do the IBM S360, which was a full-on hardware virtual machine, which he called the pseudo machine. So we thought this was kind of interesting that we're certainly not we're not breaking new ground here or anything interesting like that with the new x86 architecture. So moving on from there, there's the IBM 370, which kind of formalized more of the 360 concepts and brought a lot of the newer technology to the market. And then the Popek and Goldberg paper kind of set the rules about what a hypervisor needs to do and what it needs to act like.
Is anybody actually familiar with the Popek and Goldberg paper at all? Familiar? Okay, so we have one person. A couple of people, okay.
Yeah, so we'll talk a little bit about what the rules and the constraints of what a proper virtual machine would actually do in the next slide. Moving on from there, some of the x86 architecture proper didn't really enable virtualization to occur, unlike the mainframe days where you actually had physically separated LPAR systems that would allow for fully virtualized S360 systems. So they needed to do a little bit of work. And one of the major technological innovations at that point was the introduction of rings in the Intel 286 chip, which was kind of a step forward where people were starting to go, maybe we're going to be able to use this new x86 architecture to be able to introduce a hypervisor-like system.
What's also sort of interesting about this sort of point in history is it's kind of where deep research into virtualizing other systems sort of fell off into sort of commodity hardware. This is where we started seeing sort of cheaper attempts to approach virtualization on 286-based systems rather than having an IBM mainframe hiding somewhere in your business. But what's really interesting is right after this is there's this huge gap where virtualization just didn't seem to be important to anybody.
10 years or something.
Yeah, 10 years or 15 years, something like that. And eventually it seems to pop up again, and I think only really around 2006, which is what we're coming up on here, is where we started talking about actual hardware-based virtualization again.
Right. Yeah, so you've got a major gap from about 1986 to 1999 where we weren't able to identify a lot of virtualization technologies that were out and about. So in 1986, you probably all remember the 386 or the i386 chip came out. It actually had a virtual machine in it that emulated the 8088, 8086, the 108088, something like that. And they did that for backwards compatibility for the DOS virtual machines. So
this was also sort of the beginning of where we were getting to the point where we could have process isolations and process private address spaces. And essentially, each process got to act as though it were in its own virtual machine. And that's sort of the beginning of this, but 286 wasn't quite good enough.
So then some guys at Stanford took the step into the deep end of the pool, and in 1999 they decided to bring virtualization back to the x86, and they did some very, very complicated software programming techniques with binary translation, on-the-fly dynamic compilation of trapping processor codes and emulating those back into the hypervisor and the virtual OS. So they did a lot of heavy lifting. I'm pretty sure they used every programming language known to man to develop VMware Workstation, which was their first release in 1999. They were founded in 1998, so you can see that they really took the product to market fairly quickly. Shortly thereafter, Microsoft's close on their heels with the Virtual PC release, and then VMware ESX Server, which was one of the earlier bare metal hypervisors, was released in January 2001 approximately.
Yep, and keep in mind, like as you're getting to these initial hypervisors, these are all sort of dealing with the crippling nature of the x86 as a platform. There's a number of instructions which are considered sensitive instructions, and if the guest system were to run any of these instructions, the host system could potentially lose control, and that's where we started seeing these really bizarre methods of dynamic patching and, you know, basically trying to predict what the virtual machine was going to do so that they could patch instructions to make that happen. And this had a whole bunch of problems, and you can actually, well, I think we have a bunch of the sort of vulnerabilities later on talking about those, and then we started realizing that these are real problems. The x86 as a platform has to do something fundamentally different before somebody can actually use it for virtualization in some sort of a security framework.
Whereas back in the mainframe days, these systems were geared to do this. So it's interesting.
Yeah, actually, just to sort of jump back to the IBM-based systems. I mean, when they engineered the original IBM ZOS ZVM systems, essentially they understood that these multiple users are potentially working on, you know, military data, private data, credit card information. So it was very important to them that they could have many of these virtual machine systems, but they needed to make sure that none of these systems could actually talk to each other, interfere with each other. So that actually went into the hardware layer of things. And interesting, if you look at our plot here, the Popik and Goldberg paper actually came out after the S370, S360 systems, which were actually fully Popik and Goldberg compliant. That was a system fully capable of implementing LPARs in such a way that even covert channels, cache timing attacks, and things like that weren't even possible. And now we're sort of getting into the end of things where we're talking about x86-based systems, and covert channels, resource starvation, things like that suddenly became problems. If anybody's run VMware Server back in the old days and you had multiple VMs going, and I watched this happen with many CTF games, the CTF game ultimately goes downhill because one team spins up a fork bomb and every other VM just crawls to a halt.
Right.
But
so you can see, like, you know, moving on here, we've got this new class of processor that came out for the x86. That you have AMD Pacifica technologies and the Intel Legrand technology, and this was basically taking some lessons learned back from the mainframe days and making those codes available within the x86 architecture to prevent things like blue pill and whatnot. So again, we got the classic arms race. You know, research comes out, you know, hardware vendor responds or software vendor responds with new feature set.
So everybody knows Ring 0. You're familiar with Ring 0. So once we realized Ring 0 wasn't really good enough to handle the virtualization problem, we introduced Ring -1, and feel free to try Googling for that one of these days. It's a basically impossible Google term. Ring -1 was essentially the somewhat ugly fix to a lot of the virtualization problems. They pushed the OS down and said, okay, you can have Ring 0, but we have to have a hypervisor that runs under Ring -1. And in this case, many of those sensitive instructions are now separated from the actual Ring -1 architecture.
So here's the litmus test that most VMs are compared by. Again, so when you're looking at the, technologies or the approach that you're going to use in your organization to roll out your private cloud, or in the UK they call it the G Cloud, where the government's consolidating about 180 data centers into 6, called the G Cloud. Sounds really exciting. This kind of some of the things you probably want to ask yourself, particularly the second point here, resource control and safety. Will your hypervisor actually prevent proxy out the ask for actual physical hardware resources? That's the real #1 question. Because if you look and dig deep into the design of these systems, you'll see that there's occasionally you'll see an interesting thing where it bypasses the hypervisor from the guest OS to the hardware. So you want to go like, that might not be compliant. Maybe not the right hypervisor I want to use in my environment. Okay. So here's the hypervisor types. We got type 1, type 2. The major thing to take away from this guy is that you've got the bare metal hypervisors, which basically they use a bootloader to boot and get your hypervisor into and running on the actual silicon itself, and then they boot a management OS on top of that. And then you have the other approach, is the Type 2 hypervisor, which is actually, it boots, think VMware Workstation, for example, it boots a general OS, and then you can fire up a hypervisor on top of that general OS.
So something that's sort of interesting to go into about the differences between these two systems is that's sort of what you're shopping for when you're shopping for a cloud platform. They just label it cloud. You aren't really sure necessarily what type of virtualization they're going for, but actually on the hardware level, it seems to matter a lot. Some of the power virtualization systems, for example, we know of attacks that took advantage of the fact that it wasn't actually running on the hardware or was actually running on the hardware. So just to correct myself, for this attack that actually ran on the hardware, one attack was actually dropping down to real mode, and in real mode actually calling interrupt vector table entries. And that totally bypassed the software OS-based patches, and this caused all sorts of problems for the host-based system, and multiple hypervisors have actually crashed from this particular issue.
So actually attacking the host infrastructure from the CPU itself, the virtualized CPU.
The other thing I should probably go into here, I think we'll get into it later anyway, but once you start working with the hypervisor in this way where you have to have virtualized hardware, you have to have communications to the virtual machine monitor, you're essentially opening up another interface that's expanding the sort of the threat profile of what this system actually is presenting. So normally you would say, well, I've got these services running, I'm running a patched kernel, I'm running all of this stuff, and that's generally your security posture, and everything's fine. But in this case, you really do have another kernel, and if you actually look at how this stuff gets implemented in these systems, they really do make these calls as though they were making kernel calls. They load EAX, EBX, ECX, EDX, and instead of calling int80, they actually do an I/O port call, which is a privileged instruction which the hypervisor catches and then services it as though it were an actual kernel request. The problem with this is that we've seen this go wrong under Linux, and we've seen this go wrong under Windows, and people seem to pretend that this back-end part of the systems on some of these, the actual power virtualization versus hardware virtualization, that part doesn't exist.
Patch right here. Yeah.
Yeah.
So you've got the two types. You have full versus para virtualization, and the para virtualization is when you're actually running. If you remember, you download and install the VMware tools on the guest. That's actually modifying the guest operating system itself to be able to communicate more intimately with the hypervisor. Versus via the Goldberg and Popick paper, you want to run. They recommend running an unmodified guest on the hypervisor. The problem with that is you have a huge performance impact because you don't have a marriage of the guest operating system closer to the bare metal. So that's the conundrum that we're in, is you have to sacrifice performance for security.
And when you end up running these, many of these patches, a good example is Parallels or Virtuoso or whatever OpenVZ-based hypervisors. For example, they actually require that the host operating system be patched, but under Windows, for example, you can't go in and patch the kernel. So what they do is they actually provide a device driver for every aspect of the system, and those device drivers abstract away what actually happens, BIOS call level, and just passes the intent over through the hypercall channel to the VMM. And the VMM itself actually performs that operation. And in doing so, it actually has to simulate a number of operations to look like the piece of hardware it's emulating. So if it's an ATAPI drive or a SATA drive, it actually has to simulate some of those SATA messages, some of those ATAPI messages to let the system know what's going on. And unfortunately, these very deep protocols we've seen in actual physical hardware have problems, and in many cases we've actually seen the systems themselves, reading, a good example is an ISO image format, that image format presents as a special disk, and that disk itself becomes an exploitable path for the system itself, and that's directly to the hypervisor.
Yeah. And just so you guys know, if you have any questions while we're going through this, feel free to raise your hands, and if we're going off in some area you don't really care about, just let us know.
I rant. I don't really let anyone talk.
Yeah. So here's the basic x86 architecture, nothing new, but the crown jewels here are the MCH and the CPU, busting from ring 3 down to ring 0 at this level, and then if you can get control over the memory controller hub, then you pretty much have root on the system. So these are, if you're going to go after these machines or you're thinking about building a system, make sure that you're keeping these two pieces of architecture closely in mind for what kind of design decisions you're making on the hypervisor.
Is anybody actually familiar what the MCH hub is, what it actually does in the system? You're just too easy.
It is the Achilles heel of the system.
So in a lot of these modern systems, something that really isn't, I suppose, revealed to most people is that the memory controller hub in its own right is its own system, runs its own operating system, and actually has DMA view to the entire rest of the system. That embedded system itself actually has a number of sort of presented vulnerabilities since they talk directly to network cards and things like that as well. And these start becoming threats to your hypervisor.
Yeah. And here's our here's a